Hello, everybody, and welcome to another wonderful day of chemistry. So, today we're going to be moving on from ionic compounds to talk about that wonderful world that is molecular compounds. So, these are going to be non ionic compounds that are held together by full covalent bonds. And we're going to be talking about a little bit of what they are and a little bit how to name them. So, molecular compounds are essentially a way to describe compounds that are formed by atoms sharing electrons instead of atoms where somebody stole electrons from somebody else, which gave us ions that then say, hey, please give me my electrons back. So, in terms of naming the compounds, they actually do tend to follow a pretty similar naming structure as our ionics. The bigger difference is we now need to specify how many of each atom is present. So what we do is we add in a series of prefixes. So you'll have a prefix that tells you exactly how many of the first atom we have and then how many of the second atom we have. And we need to do this because, well, it turns out I no longer have charges to tell me what the proper ratio of these species are. So the first thing we have to actually deal with is who's my first element and who's my second element. In general, the first element should be the more metallic element. So this means the element that is further to the left and further down in the periodic table. So whoever's further down and to the left will tend to be our more metallic ion and should go first. So this will follow a lot of the same rules we had when writing out a structure. Um, Then for the second element, just like ionic compounds, we'll go ahead and use the suffix of "ide" to reference the second species. Now, that tells us about the names and the suffixes, but what about these prefixes? Well, for that, we go to, well, Latin. So if there's one of an atom present, we use the prefix mono, then di, tri, tetra, penta, hexa, hepta, octa, nona, deca. So, good way to try and keep these straight is think about shapes. Triangle, 3 sides. Tetragon or tetragram, 4 sides. Pentagon or pentagram, 5. Hexagon, heptagon, octagon, nonagon, decagon. Some people, once we get to these last three, like to think September because we corrupted the original Heptember, October, November, December, because they were originally the 7th, 8th, ninth, and 10th months. So that can be a good way to try and keep these names straight. However, an important thing to keep in mind is when we're dealing with the first element, if there's only one of those atoms present, we go ahead and omit the mono prefix. However, if there is two, we do include di. And if there's one of the second element, we do include the mono prefix. So this is all fairly confusing. So let's go ahead and do three molecules. The first two I like because they are so common, you may have even heard their names. So first we've got water. However, chemically, this is going to be, I've got 2 hydrogens, so it's dihydrogen, 1 oxygen, so it's monoxide because we use that suffix. So dihydrogen monoxide. Turns out it's perfectly safe, even if people get scared about that monoxide part. As long as the first part's dihydrogen, they're perfectly safe. Now, the second one, everybody should know. So this is carbon. We omit the mono, and it's still an oxide, but now it's a dioxide. So we get carbon dioxide, that world terror that's making the whole planet into a hothouse. Now, just to kind of illustrate how complex these binary molecules can become, let's do it this last one, P4S10, and break it down. So we've got 4 phosphoruses. So that would be tetra, phosphorus, deca, sulfide. So tetraphosphorus, decasulfide. So when dealing with these binary compounds, they're usually pretty easy to break down into naming. However, there is a special class of molecules we're going to be using a fair bit of that is important to note because they have a slightly different nomenclature. and that's going to be our acids. So first we need to kind of define what an acid is. So when push comes to shove, what an acid really is it's a molecule that contains a hydrogen atom that can be released as a proton. So that is a hydrogen cation and leaving behind an anion. When we're talking about acids, this is really what we're looking for. Something that contains hydrogen that can decompose when put into water. We'll go ahead and do a more rigorous definition next semester. But for now, this is a pretty good definition. So let's go ahead and talk about, again, naming these acids. So when we've got a binary acid like this, so it's hydrogen and something else, it's going to actually follow a fairly nice naming convention. Since the first element is hydro, is a hydrogen, we just give that a hydro. Then we give the element of the ion, and we replace the "-ide" with an "-ic". So this becomes hydrochloric acid. So we can go ahead and do this for another one. So HF, or hydrofluoric acid. And these are some that you may have seen. And again, we have hydrochloric acid, and we can walk our way through the halogens, giving us hydroiodic acid, where we now replace the chlorine with an iodine. And you can do this for hydrobromic as well and really complete the set. However, one of the things we do have to watch out for is that many of our acids are going to be ternary. So this means that they contain 3 elements instead of just 2. Most of these acids are going to have one of those elements, of course, being hydrogen because it is an acid. And then another one is oxygen, because really what they are is they're what we call oxyacids. So a good way to think about an oxyacid is they're really just an oxanion that we talked about last time, where we now have a hydrogen to counteract that negative charge. So they're going to follow the same nomenclature as the oxyanions, but now with just a modified suffix and replacing it with an acid. So what we can do is any of our oxyanions that end with an "-ite" now end with "-us acid. And anything that ends in "-ate", it now becomes "-ic acid." Because remember, "-ite", "-us", "-ate", "-ic". Okay, so let's go ahead and work some examples because this is a little bit vague. So for example, hypochlorite now becomes hypochlorous acid. So adding the H, all it does is change this suffix. Similarly, chlorite now becomes chlorous acid. And chlorate now becomes "-ic", so chloric acid. And the same thing with perchlorate now becomes perchloric acid. And it is worth noting that these become fairly common in use. So one of the important things is, as I talked about, one of the defining features of acids is that they break apart in the presence of water. They'll release a proton. However, some of these only partially break apart, and they're called weak acids. But most of the time when we're thinking about acids, we're thinking about something called a strong acid, which means they completely fall apart in the presence of water. And these are going to be the ones that when you think a good acid, you're thinking these. And there are 7 strong acids that we'll go ahead and be bringing up periodically throughout the semester. So our 7 strong acids, we pretty much start with the halogens. So we have hydrochloric acid, and then we work our way down for hydrobromic and hydroiodic. The other 4 are all going to be oxyacids. And they're all going to be oxyacids where we've essentially made sure there's as many oxygens as possible. So we have nitric acid, sulfuric acid, and then the last 2 are chlorics. So chloric and perchloric. Because again, when we have these groups towards the edge of the periodic table with nitrogen, sulfur, and chlorine, these tend to be very good acid groups. So for the oxyacids, nitric, sulfuric, chloric, and perchloric. Together, these give us our 7 acidic groups. Now, there's one last type of molecular compound I want to go ahead and bring up, and we've already kind of seen it a little bit. And so these are going to be essentially what I like to call complex molecules, where I've got two molecules that will bind together in a fixed ratio to make a solid. And one of the big defining features is that they form a fixed ratio as a solid, but they aren't an ion or an ionic solid, which is the other way we typically think of fixed ratios. And these are going to be hydrates, where I have a specific number of water molecules that will bind to a specific number of another compound in a solid lattice. So most of these hydrates, what I have is an ionic complex which binds a specific number of waters. So when we're doing this, we're going to be adding our number of water molecules to the end of the name. So let's go ahead and start with a solid with no water. So we have a white solid of copper and sulfate, which, if we walk through, should give us a name of copper 2 sulfate. Fairly good. Now, because this forms does tend to absorb a lot of waters, whenever you have this form, we very deliberately label it as anhydrate, no waters. And it can be very important because if I ask for copper sulfate anhydrate, it's important to know that this is the compound I'm asking for. Because if I have waters present, this is going to change the molecular weight. Well, this is especially important because copper sulfate also can absorb 5 water molecules to make a beautiful blue compound called copper sulfate pentahydrate. And this one is actually fairly common as an antifungal, antimicrobial. And you'll often see a lot of blue reflecting pools. The reason why they look so brilliantly blue is there's copper sulfate dissolved in there. So again, you can get a lot of changes when you add these waters. Because again, we can have a change of color, but we can also have a change in molecular weight. And again, in order to change the name, all I need to have is this last little addition of how many waters, in this case, 5 waters, pentahydrate present. If there's no waters, anhydrate. So hopefully this makes sense of the wide array of molecular species. Next time, we're going to kind of do a quick summary of a lot of organic molecules. And I'm going to be doing this so we have a good idea of what sort of biologically relevant molecules we may tend to see as examples for the rest of the semester so that it's a little less scary when we talk about them. Until then, take care.